My name is Jeffrey Frank. I am a clinical professor of emergency medicine at the University of Alberta and a visiting professor in disaster medicine at the University of the Eastern Piemonte Orientale. I have a master's degree in applied statistics from the Rochester Institute of Technology, and today I will be talking to you about general hypothesis design. Objectives of this lesson are to understand how to properly formulate a null and alternative hypothesis, and to define the two main types of hypothesis testing errors. So, a little quiz to keep in perspective as we go through this lesson is to imagine this scenario. An employee of a gelateria has developed a new ice cream additive, which is gorgonzola and anchovy. He wants to start full production of the additive to the chocolate ice cream. The owner of the gelateria, rightly so, is skeptical, as refitting the existing factory will be expensive, and he asks the employee to provide proof that the new additive will actually sell better. So I urge you to work through this quiz briefly before we continue and to just try to write down the appropriate research hypotheses for the experiment and to think about the two possible hypothesis errors in this experiment. So what exactly is a hypothesis? Well, a hypothesis is a claim or assertion about the value of a single parameter or the value of several parameters or the form of a probability distribution. This is the mathematical definition of hypothesis. So what is the null hypothesis? Well, the null hypothesis is the claim that is initially assumed to be true. This is often thought of as either the prior practice, the prior belief, or the standard of practice. And when we write this out before we start our data collection, we usually label this as H sub 0, and we'll state it as an equality. So we might say, for instance, a hypothesis about the perhaps mean of a certain value would be x equals 50. We believe that the mean of a certain value is 50. Now, why do we choose the status quo as the null hypothesis? In fact, this is very important. So this goes back to the basic tenet of innocent until proven guilty. And it is our burden as an experimenter to prove that the status quo is actually false. An important thing to remember is that the vast majority of research hypotheses are actually wrong. And so what we are trying to do as scientists is sort out the few research hypotheses that are actually correct from the big overwhelming mass that are actually wrong. And we have to keep in mind that the cost of falsely rejecting a null hypothesis can actually be quite high. Now, the alternative hypothesis is often called the researcher's hypothesis. And this is an assertion contradictory to the null hypothesis. This is usually labeled as H sub A, and it's often stated as an inequality, such as x is not equal to 50, or mu1 is less than mu2, or some proportion is greater than 0.8. And here I just want to give a few examples of suitable hypotheses. So here we might be looking at a test where we're comparing the average score on a pre and a post test. And our hypothesis would be that the average score is equal on the pre and post test. And our alternative hypothesis would be that the true average score is not equal on the pre and post test. So we might see this as an example. Perhaps we're giving a training course and we want to know that our post-test, the average score is actually higher than the pre-test. Well, let's the burden upon us as the researchers to prove that our course is actually working, and therefore the null hypothesis is the status quo of basically no effect. Here we have a different study where we're actually looking at a proportion. And here we might say the null hypothesis is that P2 equals P1, and that we might say the proportion of correct triage is equal for START and CTAS. Again, the status quo would be that the two are equal. And the alternative hypothesis might be that P2 is not equal to P1, or that the proportion of correct triage is not equal for START and CTAS. And a third example might be to look at the value of a specific number, where we're looking at maybe a simulation model and we say, well, the ideal number of beds in influenza assessment center is 18. Let's say that's what we already have in our influenza center. And our alternative hypothesis might be to say, no, it's not equal to 18. We need more or less. A basic tenet behind statistical hypothesis testing is that the null hypothesis will be rejected only if strong evidence suggests that the null hypothesis is false. And here we're looking at the innocent until proven guilty analogy. And if you remember in the legal system, as in hypothesis testing, there are basically two conclusions that we can come up with. At the end, we can either reject the null hypothesis or we can fail to reject the null hypothesis. This is very similar to the legal tenet of guilty or not guilty. And we will see here that when we can reject H0, we can fail to reject H0, but we do not say that we accept the null hypothesis. This will become clear as we look at the math. Now, alternative hypotheses may be either one-sided or two-sided. And what does this mean? So a one-sided hypothesis, one-sided alternative hypothesis, would be that we are looking for one direction, such as our null hypothesis of x is equal to 35, and our alternative hypothesis is that x is greater than 35. So we're looking for an alternative hypothesis that's on one side of the null hypothesis. Conversely, we can have a two-sided alternative hypothesis, such as a null hypothesis that x is equal to 35, and an alternative hypothesis that x is not equal to 35. Now, one thing to remember is that usually rejecting the null hypothesis in the opposite direction is useful information. And from a statistical point of view, just hoping that the new treatment is better is not enough. We can imagine, for instance, if we were doing a study to see if steroids helped in recovery from spinal cord injury. Well, it would be very important information if we actually could prove that steroids were harmful in spinal cord injury recovery. So we can see the value of a two-sided hypothesis. A general maxim is that a two-sided alternative hypothesis should be used unless there is a clear reason to not do so. Not just that you hope that steroids will help from spinal cord injury, but that there's a clear mathematical reason we must do so. A very important thing to do before you go about in your statistical analysis is to also check journal requirements if you plan on publishing your study, because the many journals actually will hold you to using a two-sided hypothesis. For instance, for the New England Journal of Medicine, the requirement is that a two-sided hypothesis is used unless the statistical methodology, the mathematical model cannot have a two-sided hypothesis, such as for non-inferiority trials. From here, I'd like to move on to talking about reduction in errors. And we're going to talk specifically about reducing type 1 and type 2 errors in hypothesis testing. In hypothesis testing, there are two possible errors that can be made. The first error is a type 1 error, which in fact is rejecting the null hypothesis when it is in fact true. And a type 2 error is failing to reject the null hypothesis when it is in fact false. To give an example of that, if we move back to the study that we had mentioned previously about the use of steroids for spinal cord injury, a type 1 error would be, in fact, to say, yes, there is a benefit to steroids for spinal cord injury, when in fact there was not. A type 2 error would be to fail to reject the null hypothesis, when in fact spinal cord injury, there's a benefit in spinal cord injury related to steroids. We can look at just a quick error matrix here, and we can see, well, on the columns we have the truth. What is the truth about the null hypothesis? And what is the test result? So obviously, if the truth is that the null hypothesis is true, and we fail to reject the null hypothesis, well, this is correct. Analogously, if in fact the truth is that H0 is false, and we do reject the null hypothesis, then again we've made the correct conclusion. If, however, the null hypothesis is actually true, and we falsely reject it, this is our type 1 error. And if in fact the null hypothesis is actually false, and we fail to reject it, as a type 2 error. What does an experiment's alpha level mean? And most of us have seen this in statistical analysis. Well, the alpha level is the probability of committing a type 1 error, or the probability of accidentally rejecting the null hypothesis if it is indeed true. Written in probability language, we say that this is the probability of rejecting the null given that the null is true. And we will also see, often written in the experiment's beta level. Now, beta is the probability of committing a type 2 error, or the probability of failing to reject the null hypothesis when it is in fact false. Again, written in probability notation, it is the probability of not rejecting null, given that the null is actually false. Now, more often than the beta error, we will see actually the term power. And in power, in statistics, power has a very specific meaning. It is 1 minus the probability of a type 2 error. Or it is the probability of rejecting the null hypothesis when it is in fact false. In general, which type of error is more likely to be harmful? Is it type 1 errors or type 2 errors? If we phrase the null hypothesis correctly, if the null hypothesis was indeed the status quo, then type 1 error tends to be more harmful. And that is exactly why we set up the hypotheses the way we do. So what are the possible consequences of type 1 error? Well, one is giving a treatment that does not work. For instance, giving steroids to spinal cord injury patients when in fact they do not work. Or retooling the ice cream factory when the new ice cream is not actually better. Or starting production of a product that does not work. And what are the possible consequences of a type 2 error? Well, this may be missed opportunity. Maybe we find that actually that steroids do work in spinal cord injury, and we miss the opportunity to improve outcomes for these patients. Maybe we don't pursue production of a beneficial therapy, or in our example case, we fail to capture increased gelato sales related to our answers. So, just to look back on our quiz, and if you recall, the quiz was related to an employee of a gelato factory who wanted to use an additive in the chocolate ice cream. So our null hypothesis would be that the mu1 is equal to mu0, or the mean of the treatment is equal to the mean of the control, or that the mean daily chocolate gelato sales are the same with and without the additive. And the alternative hypothesis would be that the mean daily gelato sales are not the same, that the anchovy gorgonzola additive either increases gelato sales or decreases gelato sales. And the second part of the quiz were what were the two types of errors. And here, the type 1 error would be concluding that the number of scoops of gelato sold is different with the additive, when in fact it is not. The consequence would be retooling the factory, when in fact there is no benefit to the additive. The type 2 error would be failing to conclude that the number of scoops sold with additive is different when in fact it is. So here we would fail to capture increased gelato sales. And here we can see, as an owner of a gelateria, the type 1 error, spending the money and investment to retool the factory when in fact there is no benefit to the additive, is probably much worse than the type 2 error, which is failing to market the gorgonzola anchovy additive. So that concludes our lesson with the objectives of being understanding how to properly formulate a null and alternative hypothesis, and to define the two main types of hypothesis testing errors. Couple quick bonus questions, because these are often a source of confusion for the researcher. What if I don't know my hypotheses? Can I make up the null and alternative hypotheses after looking at the data first? There's a question. The answer, of course, is no. And in fact, the hypothesis tests must be fully specified before any look at the data. Mathematically, the statistical tests that we're going to learn how to do not make sense if you look at the data first and then make your null and alternative hypothesis. And this is a common error that we see in research, which we often call such things as data dredging or data snooping, where we collect the data first and then make some hypotheses about what we find. What you will find is that your chance of making a type 1 or a type 2 error are drastically increased. This is often the source of making false conclusions and spending unnecessary time and effort pursuing solutions that are in fact not effective. So the answer is no. You must specify them before any look at the data. And the bonus question 2, we haven't talked about p-values and confidence intervals yet, but many people make these and wonder, Can I make them without having an alternative hypothesis? Or, to specify in a different way, can we just not have an alternative hypothesis and just make p-values and confidence intervals and see what we get? The answer, of course, is no. The answer is, from a mathematical point of view, whenever you have a p-value or a confidence interval, you have a hypothesis test. And even if you don't explicitly specify it, even if you're not aware of it, there is a null and alternative hypothesis associated with that test. And that concludes our lesson in hypothesis design.